Is a basic introduction to the different kinds of energy that we're going to be working with in physics. Energy is one of the most fundamental concepts we look at in physics. Energy is very similar to what you might think of as the money of physics. Money gives people the ability to do things, buy groceries, take vacations, receive services. Well, energy is what allows objects or system to undergo change, such as changing speed, changing temperature, or changing height. With few exceptions, any time an object or system undergoes any kind of change, it's because there is some kind of energy transformation that took place. Now, energy transformations can come in many, many different forms. For an example, an energy transformation could be energy transforming from one form to another. For example, on the roller coaster, energy is transferring from gravitational potential energy into kinetic energy. In the image with the solar panels, energy is transforming from light energy into electrical energy. Or same thing, there's the kinetic energy of the wind that transfers into electrical energy in the wind turbines. We could have energy being transferred from one object to another. As all of the particles collide, energy is being transferred from one to another within the collision. The woman is giving a push to the child and transforming the child into now having kinetic energy. She's moving. Energy can be transferred from one system to another or between systems. And an example of both of these could be considered the fire that is transferring energy into the pan of water from one system to another. Now, energy is measured in a unit called joules. And joules have like newtons. So newtons or kilograms times meters per second squared. Well, a joule is similar. A joule is another kind of summary unit, and a joule is sometimes called a Newton meter, or it could be a kilogram times meters squared per second squared. So these are the breakdown units for joules. So energy is measured in joules. And like money, energy is a scalar quantity. We don't worry about any kind of direction associated with it. So all of those particles that were bouncing around, if you learned in chemistry about kinetic molecular theory, then that's what's going on. We're just taking the sum total of the kinetic energy for those molecules, and that's actually temperature. So it's possible in some cases to have negative amounts of energy, which is like having a negative amount of money or having a debt and owing money somewhere else. If I have negative energy, it just means that I owe energy for, somewhere else. Now, some important forms of energy that we're going to be looking at in this class. Kinetic energy is the energy of motion, and the variable for kinetic energy is a capital K. We have gravitational potential energy, that's U sub g, and that is a form of stored energy associated with an object's height above the ground. We also have elastic or spring potential energy, U sub s, and that's energy stored when a spring or other elastic object is stretched or compressed. You notice that both of these are capital U's with a subscript. The capital U is just the general term for potential energy. And then the subscript just tells you what kind. Now, these three forms of energy are the ones we're going to be focusing on. The above forms of energy together are known as mechanical energy. Some other forms of important energy that we might encounter at some points is we do have thermal or internal energy, and we will deal with this one a bit. And that's just because of the molecular vibration, which is what that picture of all the particles bouncing around was. The more the molecules vibrate, the greater the internal energy and the higher the temperature. Chemical energy, that's the energy stored in the bonds between molecules. Nuclear energies, energy stored in the mass of the nucleus of an atom. We have electric potential energy, energy that's stored by the separation of charge, and we'll deal with this a little bit in the spring. Light energy is energy carried by a light wave. Sound energy is energy carried by a sound wave. We're going to specifically go over the three forms of mechanical energy that we're going to be focusing on. Kinetic energy is the energy that a moving object has simply because it's moving. And the kinetic energy of a moving object depends on two things, mass and speed. So when we think about, well, with kinetic energy is proportional to mass. That means that if I double the mass, it doubles the kinetic energy. Mathematically, kinetic energy increases as the square of speed. If the speed of an object doubles, its kinetic energy is going to be 4 times greater. And that comes from our kinetic energy equation, which is K equals 1/2 mv squared. Now, potential energy, in general, is stored energy that can be readily converted to other forms of energy, such as kinetic or thermal energy. An object by itself cannot have potential energy. Potential energy is dependent on an interaction between objects, some kind of system. Now, kinetic energy is different. Kinetic energy is the only form of energy, is the only form of mechanical energy that an object can have when it's by itself. In order to have any kind of potential energy, the object has to be part of a system. So if I throw a tennis ball, if I just look at the tennis ball can have kinetic energy. But if I'm throwing the tennis ball and the tennis ball is above the ground, it cannot have gravitational potential energy unless the ground is part of my system. So potential energy requires your object to be part of a system. And forces that store useful energy are called conservative forces. And those would be our gravitational potential energy, our gravitational force, and any kind of elastic force. Forces such as friction cannot store useful energy, and they are called non-conservative forces. Anytime we have a non-conservative force, then something called the path taken is going to matter. We're going to talk about this a little bit more later on. The gravitational potential energy is the energy that exists because an object with mass is separated height above another object that creates a gravitational field. Basically, what that means is that gravitational potential energy comes from the person being above the ground. And generally also because of the ability to change that height. As the object gains heights, becomes more separated from the Earth, the gravitational potential energy increases. Now, this is the equation for gravitational potential energy. And one thing to be very aware of is that the equation includes the delta, the change in. So when we're talking about gravitational potential energy, we're really only interested in changes in gravitational potential energy. And because of that, we can choose the reference level where our gravitational potential energy is 0, since only those changes matter. And because gravity is a conservative force, gravitational potential energy depends only on the height of an object and not on the path the object took to get to that height. So a way of thinking about this is if I'm at school and my classroom is on the 2nd floor, and so if I'm here and I'm holding a tennis ball. Well, technically, the tennis ball is all the way above the ground from the very far ground. And so I could say that the height of the tennis ball is, say, 5 meters. It's probably more than that. I'm just making up a number. But the tennis ball can't fall through the floor here. So rather than looking at the height all the way down to the ground, it's more useful for me to look at the height just to the floor within my classroom. And so I could say I'm only holding the tennis ball 1 meter above the ground because that's all that matters. This is all the gravitational potential energy that then could convert into other forms of energy as the ball falls. So that's what we mean by where we can choose our 0. We choose the 0 height that is the most convenient for the problem. So the change in gravitational potential energy is proportional to the change in height. So if I double my height, I double the gravitational potential energy. If I double my mass, I double my gravitational potential energy. So gravitational potential energy is proportional to both mass and height. Now, elastic or spring potential energy is stored when a force compresses a spring or stretches a spring. Now, the way we look at that force is through something called Hooke's law. Hooke's law describes the force required to compress a spring. And this is the distance the spring is stretched or compressed, and this is something called the spring constant. The spring constant basically just describes the resistance to stretching or compressing a spring. But if you think about a spring, what it really is how hard is it to stretch or compress that spring? So if you have a spring that is very, very difficult to compress, then it's going to have a very large spring constant. If you have a spring like a slinky and it stretches very easily, it's going to have a very, very low spring constant. So the spring constant is just how difficult is it to stretch or compress that spring. It's just a mathematical way of describing it. So elastic potential energy is stored in a spring. The elastic potential energy stored in a spring is the energy that exists because a spring is stretched or compressed from its natural length. So if you let a spring just sit, it's going to go to its natural length. And from there, or at that point, it doesn't take any force to do anything to it. That is without any kind of force doing anything to it. As soon as I apply a force to compress it, that distance I've compressed it from its equilibrium is going to be our distance x, the compressed distance. Now, potential energy increases if the spring is stretched or compressed further from its natural length. So again, this x is how far it's been compressed or stretched from its natural length. K is the spring constant, and this is the equation for spring potential energy or elastic potential energy. Now, a way of experiencing this is that we can also model the elastic potential energy with something as simple as a rubber band. If you take a rubber band and hook it around both of your thumbs, if you stretch that rubber band, you can feel that the more you stretch it, the more the force pulling back is, the more energy that's stored in that rubber band. If you release that rubber band when it hasn't been stretched very much, it's not going to hurt your thumb very much. But if you stretch it really far and let go, it's not going to have a direct ratio. It's going to have an exponential increase in the amount of pain it's going to cause in your finger. So what you're going to do the rest of the day is you're going to work on just some simple calculations with these three equations.